Hello everyone, and welcome to Chapter 15 of our STEM Challenge course. It's on communities and populations in ecology, and we'd like you to read all of Chapter 15. This is going to be our last chapter for the course. So in 15.1, we talk about community interactions, and really what they're talking about here are the interactions between different species. We'll be looking at community as the term is used in ecology. We'll be looking at a relationship called predation, which affects the population size and evolution. We'll look at interspecific competition. We'll look at terms called mutualism, commensalism, and parasitism. These are different types of relationships within an ecosystem. And then there's a term in this section called succession, primary and secondary succession. So we'll be looking at what that means. So a community is the biotic part of the ecosystem. It consists of all the different populations of all the different species in the same area, and it includes their interactions. So interactions are a big part of this chapter. Here's an interaction. It's called predation, and we see that we have a couple lions here feeding on a zebra that they've captured. Predation, I know this is a gruesome picture for some people, but what an ecologist sees here is energy moving up into the food chain. There's also a species called the keystone. Certain species are called a keystone species, and they play an important role in a community. And if anything happens to that keystone species, sometimes there's a ripple effect throughout the ecosystem. Make sure you read about that. Adaptations, predation. We know that camouflage is quite a good way to camouflage yourself from someone who's going to eat you. Make sure you read about adaptations to predation. And we're going to look at different relationships, symbiotic relationships, different species. One is mutualism. There's a really interesting relationship between these two species, between this shrimp, that's a shrimp that you see in the foreground there, and this fish in the background. You'll read about that. The term ecological succession means that communities are not static. They're dynamic. They're changing all the time. And I'd like to give you an example of primary succession. So let's say a volcano blows up and there's just hardened rock around most of the area. When life returns to that, that's an idea, the idea of primary succession. It means that when you have bare rock and life slowly moves back onto it. This is our animation. You've already seen this. If you don't remember this, please watch it again. If you do, don't worry about it. We also have a great animation is Will the Ocean Ever Run Out of Fish? It's a great conservation issue. We wanted to raise these in our last chapter. Take a look at this animation as well. And some of the adaptations that squid have to outsmart their predators. Okay, in section 15.2. When ecologists study populations, they're looking at things like population size, its density, and its dispersion. That means how it's spread out. We're going to be looking at some population pyramids and things called survivorship curves. And we're going to be looking at factors that determine population growth rate. And we're going to be looking at the difference between exponential and logistical growth. So make sure you read this carefully. This is three diagrams here, clumped, random, and uniform, different ways that a particular population can be spread out in an area. That's actually rare that it's totally uniform. Usually it's clumped or almost semi-random. This is a population pyramid. This is a population pyramid of a human population. And we have all the females on the right. We have all the males on the left. And you'll notice that these normally are in 5 or 10-year increments as we go up. As we go from here, newborn to old, elderly, and how many births we have. Population pyramids for every country on our planet are very, very different. And they reflect some of the changes that are going on in the country. Besides the population pyramid, we also have what are called survivorship curves. They're important to ecologists. And this shows you type 1, type 2, and type 3. In type 1, we have a low death rate. Many individuals live to old age. That's very similar to what we have in the United States. Look at type 3, high death rate. Many individuals die young and few live to be old. And depending on where you are in the world, your country might reflect that. And here we have a moderate death rate and birth rate at all ages in the type 2. Population growth rate is determined by this equation. So R here is the population growth rate. This is the birth rate plus immigration rate minus death rate and emigration rate. Make sure you know this. We're going to talk briefly about exponential and logistic growth of a population. So for example, right here, this dotted red line defines the carrying capacity for a specific population. So think of an area, let's say around where we live. We have mice, we have lots of mice. So this B curve here represents logistic growth, and this mouse population has reached its carrying capacity and would go along here. But this curve, A, shows us exponential growth of the mice, and that could be caused by a lot of different reasons. So make sure you read this and understand this. Human beings, as you'll see pretty soon, human beings on our planet are experiencing exponential growth, and it's been that way for the last couple hundred years. We'll see that in a second. So in 15.3, we talk about the human population. We'll talk about early human populations and the demographic transition that's been happening. So here is a classic view of population of the world in billions. So let's take a closer look at this. So if we take a look at this one, this was 10,000 BC, 8,000 BC. Notice it's taken human beings a long time to reach 1 billion people on the planet. It's right here in around 1800 AD. But then, look, it took just a little bit of time, 200 years, for us to grow exponentially. And where we are today is over 7 billion people, not 6 billion, 7 billion people. I have a more detailed population graph I'd like to show you right here. This is the same graph, but with a few more details. Notice what's happened. That in 1900, we were at about 1.6 billion people. In 1960, we more than doubled that, and then we doubled it again in less than 30 years. So right now, human population is experiencing a lot of growth. Some ecologists and some people that study human populations say that it will start to level out at 9 billion people, that's the carrying capacity for the planet Earth. This part of your text talks about early population growth, and when we read chapter 1 of Sapiens, they reviewed some of this, but I'd still go through this and make sure that you understand in general terms human evolution and population growth over the last couple 100,000 years, just the big picture. This is a diagram that shows you stages of demographic transition, and let's go back to that. These are deaths per 1,000, and these are births per 1,000. And take a look at what happens over time if you're a stage 1, in stage 2, stage 3, stage 4. So relate that to the graph. Interesting that every 10 years the United States takes a census, and in 2011 Time.com published a What Will the World Look Like in 2050. Here's some of their comparisons, or I'm sorry, some of their predictions. India will become the most populous nation, surpassing China in just a few years in 2025. The U.S. will remain the third most populous nation, and take a look at what happens in Japan and Russia and Nigeria. Some more interesting things about predictions about what this will mean. Now, because we've had this incredible growth in human population, human beings are living in areas where we didn't used to live before, and in a lot of cases we are moving out other forms of life. And many ecologists talk about a biodiversity crisis, and that crisis is how do we keep a rich mixture of the life that we have on our planet, whereas human beings, as they move into some of these areas, will crush that life and cause lots of extinction. So I'd like you to read about the biodiversity crisis. We have an animation and a talk about it. A lot of people think that we have to do 100% preservation of our planet, and other people say, nope, we can't preserve everything, we have to do 100% development. But you've heard recently the term sustainability, or managing our resources so that we can maintain them for the future. This is really kind of, I think, the area that we really, really need to look at closely. How do we make living on this planet with lots of people sustainable? We have to do it in a smarter way than we've done it in the past. So read about biodiversity and what it is. They'll talk here about all the species that we don't see, and there's lots of species of life out there. This is a really interesting chart that I'd like you to look at. So on the left here, we have the number of known organisms. They're posting it as 1.8 million species. Really difficult to say what that number is for sure. It's probably more than that. But look how it's divided. We have eubacteria, protists, fungi, plants, and then animals. But if we look at animals over here on B, and they're saying we have approximately 1.3 million species of animals. Most of those animals, I'm going down here to insects, most of those animals are insects. And you can take a look at fish, amphibians, reptiles, and mammals. They all fit over here, and then other types of animals in here. But most animals are insects. Let's take a look at plants. We talked briefly about this on the chapter of plants. Plants, we have about a total species of, let's say 300,000. They have 287,000, but let's go with 300,000 species of plants. We have conifers. Those are pine trees that we know them as pine trees. Ferns, mosses, flowering plants, which are monocots, and flowering plants that are dicots take up more than 3/4 of all the plant species. Remember we said how successful flowering plants have been on the planet. So make sure you read in your text why biodiversity is important, and they have a nice little description here of the economic benefits of biodiversity. And also become familiar with ecosystem services and what that means. Ecosystems serve us lots of important things, and they list a few of them, not all of them, here in your book. We hope we're not going through another mass extinction, but a lot of ecologists say we are. Read about that. The Encyclopedia of Life is an online encyclopedia that's trying to catalog all the species of life that are on the planet right now. It's a really interesting project. That ends our chapter, and I'd like to recommend a couple books to you. If you're interested in science in general, there are 2 books by a wonderful American writer. His name is Bill Bryson. A Short History of Nearly Everything. Really, really well done. If you're going into anything with anatomy and physiology, you might want to look at his other book, The Body, A Guide for Occupants. This just came out in 2019. Another wonderful talk is a cancer doctor from Colombia by the name of Siddhartha Mukherjee, and he wrote a Pulitzer Prize-winning book called The Emperor of All Maladies. If you are thinking of going into healthcare, great book. He also wrote another book called The Gene, An Intimate History. Please, good luck. Let me know if I can help in any way, and I gave some screenshots and links to, these are 3 YouTube teachers, one for biology, one for math, and one for chemistry. This is Marcus Brownlee. He's a wonderful YouTube teacher about technology. If you don't know about his channel, check that out. And PhET has wonderful simulations for learning science, a little bit of math, but mostly science. And Hybrid Medical Animation is a company that makes great illustrations, animations, and demo reels for biology. Anyway, I just wanted to mention those randomly at the end. I hope you're doing well. Please study for the quiz, and we'll see you soon.